Right. So in the previous lecture, we have already discussed about this abstract data type specifications, right? I mean, this contains certain sections. Like first section will be the type that you need to mention. What is the type? I mean, you have to declare the type of the object or the class. Okay, and then you will have certain number of operations, right? So the operations can be, maybe it's a query operation, or it can be, it can be partial operation, right? Or, we have already classified, right, certain number of operations, right? So now the first section type here, we create a, I know we define the object type, right? So it's a stack of type G, right? And now the operations are like this. So here is a new stack operation. Okay, so by using new stack operation, you can create a stack. That means it is going to create a stack of type G, right? Similarly, you can have a operation like push, right? So for this push operation, you have a stack. Okay, and then you have to insert an element into the stack, right? That means you wanted to push an element onto the stack, right? So usually after pushing an is going to return you again a stack with that element G, right? So this is what, right? So there you try to, you try to, manipulate the stack. Okay, so now there is a pop operation. Okay, so similarly you wanted to, pop an element from the stack. Okay, after popping an element from the stack, so it is going to return you again the stack, right? So the top element will be popped out, and then after that the stack will be returned. Okay, and similarly there is a top operation through which you wanted to know what is the top element, right? What is the top element? That is, so you need to give a parameter, to give a parameter. So ultimately it is going to give you the element. What is that element that is there in the top of the stack, right? So that is the reason why it is going to return you an element, right? So in the pop case, so it is going to return you an stack. Similarly, there is a isEmpty operation also. So you can see, so this isEmpty operation, it's a query operation, right? So yeah, what it is going to check whether a particular stack is empty or not. If it is empty, so it is going to, if the stack is empty, then it is going to return a boolean value. Boolean, maybe it is going to return a true, right? So if the stack is not empty, so in that case it is going to return a false, right? But you see here, this query operation is not going to return any object of type G. Okay, neither it is returning the object, or it is returning an element of type G. Okay, so it's something else, right? It's another variable, true or false. Okay, so keep this thing in your mind, right? Now you are similarly, there can be a precondition, right? Whenever I told you, so the partial functions, right? So you can apply pop only when there is only when there is an element. Okay, so you cannot pop an element from the empty stack. Okay, that's an error. So it's a precondition you need to meet, right? Similarly, you have certain number of axioms, right? So if you are going to create a new stack, okay, so if you apply new stack, okay, if you apply these operations, okay, whatever the atomic operation here, new stack is one atomic operation, okay, so or the function, right? So this operation is applied onto a query operation, right? So now isEmpty is what going to give you, so it always going to give you true. Okay, so because whenever you created a stack, so the stack will be created with no elements. Okay, unless or until you pushed an element onto a stack, so now stack will contain no element. Okay, so it is always true, going to return. Now similarly, if you apply a pop operation onto a new stack, it's going to give you an error. This could be one axiom. Okay, the other axiom can be top of new stack. Okay, so if when you created a new stack, at the top of the stack is no element, right? You do not have any element, and you wanted to return an element, right? You wanted to know the top element, so definitely it is going to give you an error. Okay. Now this is exceptions. Okay, these are the exceptions case. So I told you in the previous section. So usually whenever you going through any algebraic specification, so usually you will have a exception section and you have a rewrite section. So these things, okay, either you can have separate sections or you can have you can both these sections can be part. So it is. So now you can see something like this. Okay, there is a new stack. Okay, so when you apply new stack, so usually it is going to create an empty stack, right? And that empty stack onto which you pushing an element G. Okay, so this push operation is going to push an element onto the new stack, right? So ultimately, so if you apply the top function to that particular stack, because push operation is going to return a stack, right? It is going to return a stack with element G. And if you see, if you apply the top element, definitely it is going to return the G. Okay. So this is the way that you can have certain number of axioms, right? And now these, so this is what, now you can apply these axioms. Okay. Now you can apply these axioms to prove, to verify, okay, or prove any expression. Okay, you can verify any expression, right? So now let's say there is an expression of like this. Okay, top, pop, push, pop, you know, this sort of thing. So and finally you have some sort of atomic operations here, new x4, x5, x6, x7, something like this. Okay, so that means this is one expression, right? You have one expression. Now, if you apply this expression, if you evaluate this expression using all of your axioms, so it will always, you know, it will give you a element maybe x4. Okay, you can apply this operations onto top and push operations, right? So now you want to try something like this, you can start from evaluating from here. You can see something. So if you apply push of new comma x4, what it is going to give you? It's a stack, new stack onto which you have pushed x4. Okay, so this till this, so it is going to return a stack with element x4. Okay, now again what you are trying to do is, you can think of now again you wanted to push x5 with x4, wanted to push again x5. Okay, so till this you have evaluated, right? So you, if you keep on evaluating this expression, so the value is going to give you is x4. Okay, so this is true no matter what representation of the stack that you choose to implement it. Okay, so now thing is that here, so when we talk about any abstract data type, I told you before also, right? So we hide all implementation details. There you will be only knowing what is an object of class, you know, some type, and it contains certain number of operations. Okay, through the certain relations among these operations, so we try to you know, you make some state changes, right? But here only we are interested in what sort of operations, okay, we have. Okay, and what sort of data that we have, we can apply onto those operations, right? So that is what abstract data types, right? So we have seen abstract data type like a stack. Okay, so now we have not talked about what representation of this particular stack is. Okay, whether the stack is implemented using a linked list or whether it is implemented using arrays. So we have not discussed about that. Okay, only what we have seen is we have seen certain number of axioms. Okay, and by applying these sort of axioms, now you can verify any sort of expressions, right? That means, so you can specify any sort of requirements using those all expressions. Okay, any doubts so far, students? Students, anyone has any doubts so far? No. Okay, fine. So now So if you so we wanted to bring this abstract data types to even classes. Okay, when you are going through any object-oriented design, so usually you can have abstract data types always. Okay, like stack is one abstract data type, right? Now you can bring that into a classes. Okay, so usually the classes are the modules in any object-oriented system design. Okay. So talk about any object-oriented system, so usually you will have certain number of classes, right? So now you can map these abstract data types to classes, because classes also contain certain number of operations and data items, right? So now this is what exactly we say. So classes can be either of two. Okay, maybe it is a deferred or it is a effective. So when you say a class is a deferred, that means it is partially implemented or it's abstract. Okay, so you can see there is a concept called abstract class. Okay, there is an interface. Okay, in if you talk about any Java programming language, so because that's an object-oriented programming language, right? So there you can see that there is an abstract class. Okay, so that means the operations are not fully implemented there. Okay, and if you talk about any effective classes, that means the operations or the methods of those classes are implemented fully. Okay, so you have a concrete methods. Okay, so that means the implementations must be there. Okay, so the implementation, right? So you can specify any classes also, right? So we just try to see how these abstract data types, right? So now abstract data types and information hiding, right? So the public part of any abstract data type, you see these specifications only, right? So they are very public, that is open to everyone, right? Whatever the operations that you have seen there, right? So like stack, if you see a stack, so what data item or what is the type of that particular stack, right? And what are certain number of operations, okay, it can have I know that's what you have seen the certain number of uh, axioms also you have seen, right? So that way you have everything, but there is a some. So part here is so the choice of representation, right? So how you going to implement that particular function or the operation is not known to any one of us. Okay, so that is the secret part. Okay, public part is all of these specifications. Okay, so that means there is a concept of information hiding. So the information is not open to everyone. Okay, so that is what. Okay, so information hiding is an important aspect of software modularization. So now this sort of this is again an important concept which can be applied onto modularization, because I told you when you talk about software architecture, right, you see certain number of modules, right? So it contains all different modules, and these modules, right? So now these modules are going to interact with each other, right? So what is the really required is the public part is open to everyone, right? But the secret part is not open. Okay, so only so here you try to do which module is to implement modules. The detailed implementation of the functions or the modules need not to be exposed. Okay, so that is not known to the other modules. Okay, so that is what we call as information hiding, right? So now we try to see the completeness of a specification. When can you say that specification is very complete, right? So before that you need to know a little bit, right? As I told you, so if you can have any expression. If let's say there is a expression, and that expression can be okay. So that expression in a proof in the previous slides, right? So if you can do so, okay, so that means almost we can say that we are going to achieve completeness of specification, right? So now So here, so we need to have well-formed expressions. If the expressions are not well-formed, then it's very difficult, right? So in order to understand, in order to answer this question, like the completeness of specification, so basically, so there should be a provision through which you should be able to prove, you should be able to prove the, you should be able to prove the expression, right? That is a correct, okay, and the expression should be a well formed, okay. So like for example, you can see here push of G. Do you think that it is a well formed? No, it is not a well formed. Why? Why it is not a well formed? Can anyone tell me?
Sir, it does not say anything about G.
It
Sir, stack is
doesn't.
not given.
Yes, 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 because you see, you going to push an element, that's it, okay? But where you going to push an element is not given, right? So that means this is not a well-formed expression, right? So the expression that you have should be a well-formed, okay? So that is what I say. So first you need to have certain number of axioms, okay? And the expressions are well-formed, okay? So here if you see top of new, so do you think that it's a well formed?
It
Right.
will
So
generate an error.
it can generate an error, right? Okay. So fine. So now you can think of, right. So whenever you are going to answer this completeness, first two things that we need to see. So there should be structural integrity as well as semantic integrity. That means so that should be structurally correct, okay, and it should have a correct meaning, okay. So the meaning, if structurally it is not correct and the meaning is not, so it will be very uh, you know check any of these these expressions, okay, whether the expression is correct or not, right? So you will understand in the next slide probably. If you do not understand now you can see here. So we have all different axioms, right? Push, pop, and all those things we have defined in the previous slides, right? Now, let's say, for example, I wanted to have replace item. That means I wanted to replace an element of stack. Okay, so I wanted to replace an element of stack with another element or another value, right? So that means I wanted to replace a value of a value um, uh, one of the element of a stack, right? So now, so for this, what would be you see? So this can be like this. So you have a stack, okay, and you wanted to replace an element G of type G, okay. So you wanted to replace an item in a particular stack, right? So then ultimately what it is going to give you, it is going to give you a stack, okay. So now this is one, it looks like a well formed expression, right? This looks like a well formed expression. Now this well formed expression can be proved by using certain number of atomic operations like the axioms, okay. Now how you can going to prove this? You can see, first thing is that you need to check that is empty is equal to false. That means whether the stack that you have, okay, first you need to check that the whether stack is empty or not. If the stack is empty, that means you are not allowed to replace any element, because there is no element. So how are you going to replace, right? So that means is empty should be false, okay. That means true, false, okay. So empty is not empty, that means there is an element in the stack, okay. So if this condition true, okay, now what you try to do, we are going through this expression, right? So what you do, so first you try to pop an element, okay, you try to pop an element from the stack, okay, right? That means first you going to pop that top element of the stack, okay. after popping that element, what it is going to return? This pop operation. What is going to return this pop operation? Anyone?
Topmost element of stem.
No, that will be popped out. Okay, but ultimately what it is going to return?
Stack.
Stack, right? True. So it is again going to return the stack. So element is popped and then the left out stack is returned, right? That is a pop operation. So now that stack, now the element is popped out and you have the stack with the popped out element. Okay. Now you wanted to push again an element G. That means you wanted to push this particular element. So that means what you are now, what it is going to give you? This operation,
Updated state.
it is going to give you what?
Update.
Rohit,
Hello.
you are saying something.
I'm not audible, sir.
You are not audible. Okay.
Okay.
Fine. So now, so you can think of like this. Okay. So here, what you were saying. So exactly, we can prove this. So ultimately, you see this. The element is popped out and then you inserted the whatever the element you wanted to replace with, right? So that means it is this push operation is also going to return a stack. Okay, so ultimately you can prove this. Okay, so replace item. Now replace item is a compound operation where is empty, push, pop are atomic operation. By using these atomic operations or the exams, now you can prove any well formed expressions. Okay, this is the way that this is the ultimately what we say. So it is syntactically meaningful expression and semantically correct also, right? So that means we can prove that it is correct, the syntactically as well as meaningfully this statement is correct. You can prove, right? Any doubts so far, any student?
Hello, sir.
Yes, Susri, ask me.
Am I audible, sir?
Yes, you are. You are audible, right? Tell me.
Then, sir, can we categorize the stack as the effective entity, right?
Stack is. Can you repeat?
Sir, can we categorize the stack as an effective abstract data type, like as all these operations are clearly been implemented?
You see, it's a abstract data type. How you are going to implement that is, as of now, we are not talking, right? What we are talking here is what are different operations, ultimately what it is going to return. Okay. So like it is a black box. Okay, it's a kind of black box, right? Specification. So you do not care about the internal details of that particular operation. Okay, what it is going to tell you is, you see, so replacing an item means through this what you understand. If somebody write replace item stack of G, comma G, it is going to return stack of G. What do you understand from this? So that means there is a stack. Okay, there is a stack. Okay, you wanted to you wanted to replace an element in that particular stack. Okay, so that is exactly going to give you a stack with replaced element. So this is the statement. How you going to, whether you use arrays or whether you going to implement using linked list, though these things are not known. Okay, here what is known is different operations and you try to prove those operations. Okay, whether these expressions are correct or not. Is it clear?
Sir, actually, I was talking about the slide number 65. There you have written classes can be categorized like like default classes and effective classes. That was my
Right.
doubt. Like I was asking if we can categorize the stack class as an effective class or not.
No. Actually, we are saying, right, usually part of classes, part of classes. So there can be two types. Okay, one can be deferred and the other can be effective. Okay, so that means either it can be fully implemented. Okay, so that means there is a must in implementation. That means you have an implementation but the deferred one is a useful in analysis and design. Okay, now we are talking about specification, right? We are at the requirement analysis, right? So this partially implemented or abstract ones are the usually useful for us. Okay, we do not care about much of the implementations, right? As of now, do you understand?
Okay. Yes.
Yes, yes. So I said there is a in a class can be of two type. Okay, so it can be deferred or it can be effective. But usually when we are talking about specification, so usually you will not be interested in this implementation part. Okay, but somebody will come up with their implementations, before and also. So maybe giving some pseudo maybe useful. Not how we go. We try to see that whether the specification is written very correctly using some formal methods. Okay, so now the definition here is sufficient complete. What is the conditions for a sufficient completeness? So when can you say that a particular object of type or the abstract data type specification is complete? Okay, so now, so what I say, so first and foremost thing is that if and only if the axioms of the theory make it possible to solve the following problems, right? So now for any well-defined expression, well-formed expression, okay, as similar to the previous one we have seen, top up, push up, x1, x2, x4, so on. So ultimately the result was given as x4, right? So that can be one well-formed expression right there. Now, what we say is, so if these two following expressions, if these two following expressions are met, then you can say that the specification is sufficiently complete. Okay, so now the first here is first problem here is you should be able to determine whether the expression E, that means the expression E should be correct. Okay, so how can you prove that the expression is correct? So this is the way that, okay, now let's say this is an expression. Now you can think of, okay, maybe you can apply replace item only. This is simplest one. Okay, so now this can be proved, right? This particular expression, it's actually not the expression, it is one of the equation or the axiom you can say, but maybe you can have a well-formed expression there, push off, replace item, something like this. You can have a well-defined expression as similar to the slide number you can see. Okay, here you can see. Yes, you can see here in this case. So top, push, pop, certainly operate. Some sort of operations can be applied. To different so as to so expression. Now can understand what is a expression, right? Now, so these expressions can be proved like this. Okay, so part of that expression, maybe you will have a smallest individual operation, this sort of operation. Okay, so if you can prove each and every operations of those that expression, that means ultimately you can prove that particular expression. Okay, that should be syntactically meaningful as well as semantically correct. Okay, this way. Okay. So the first condition is you should determine whether E is correct or not. So something should be syntactically and semantically it should be correct. And the second thing is if the E is a query expression. Okay, if that E is a query expression, that means it is a kind of as I said so query expressions or the query operations, what they actually return. So they are not going to return either they are not going to return any object of same type, object of T, or it is not going to return any element of that type. So can you remember what is that query operation we talked about? Can anyone here tell me which query operation I am talking about now? Which one? Satyendra?
Is empty. We have talked in stack.
Yes, we talked about the is empty, right? So is empty is not going to return either stack or not. It is going to return any element. Okay, but what it is going to return? It is going to return something else. Like it's a Boolean value, true or false, right? So that is we are talking about. If that is a query expression and has been shown to be correct under S1, that means that that expression is correct under S1. I mean it follows S1 condition, as well as it is a query expression. Then in that case, express is value under a form not involving any value of type T. That means that is not going to give you. So you try to evaluate that expression. So ultimately it is going to give you some value which is not involving any value of type T. Okay, that means neither it is going to give you the object of type T, or neither it is going to return you a value of type T. Okay, so it is going to give you something else like maybe Boolean. Okay, so you can think of this is the way. Okay, or because that is going to give you sometimes error also, right? So error or maybe true or false. So those can be some query operations you can think of. Okay. Okay, if these two conditions are met, then you can say that the abstract data type is sufficiently complete. Okay, now the other one here is so when can you say that abstract data type specification is consistent? That means the specification consistent if and only if, okay, for any well-formed query expression E, okay, let's say you have any well-formed query expression E, the axioms make it possible to infer at most one value for E. Okay, so that means, so when you evaluate that particular well-formed query expression, always it is going to give you at most. Okay, it's not two different values. That if it is going to give you two different values, that means what? That means the expression is not consistent. Okay, it is you know, it is at one point of time it is saying something, the other point of time it can be saying something. There will be a scope for multiple interpretation. Okay, so that should give you only one unique value. Okay, so that means at most one value. So in which example we have seen this at most one value? Can you tell me?
Is empty returning Boolean value?
No. What I'm saying, so when you evaluate any query expression, okay, by applying all these axioms, okay, so that query expression should always give you at most one value. Okay, at most one value means what? Only one value. Okay, it should be going to give you one value or not. It is not going to give you any value. Maybe it is going to be error, okay, or something else. Okay, so what I'm saying is, so it should always have at least at most one value. Okay, but if it is going to give you at least one value, what will happen? Or more than one value, what will happen? In which example we have seen? Can anyone tell me in which well-formed expression we have seen at most one value it is going to give you? Any student? Huh? Yes, Susri, tell me.
So top gives one value.
Okay. That is fine. Okay, so but now because I am talking about here the well-formed expression, so expression contains certain number of atomic operations. Okay, it's not a single operation, right? So that is the way that we are going to specify any requirement. Okay, So you have certain number of operations, right? Now you say, I said you, right? So now if you have this top, that means this particular well-formed expression, so it contains certain number of operations. It's not only one operation applied. You can apply hundreds of operations. Okay, so you can expression can have hundreds of operations, but ultimately when you evaluate this, what is it going to give you? So it is going to give you x4 only. It is not going to give you x5, x6, x7. If you either you evaluate from left to right or right to left or whatever the mechanism you apply, always this is going to give you only one value. Okay, at most one value. That means now this is what we say. If it is that that's not a consistent. Okay, so it should always give you at most one value. Okay, do you understand now? Any doubts so far, students? Consistency? No. Is it clear, all of you?
Yes, sir.
Okay. Okay. So now we'll see another example here, Unix directory. Okay. So now you can specify an Unix directory. So using abstract data type specifications, now you can see here how it can be. So the type here is Unix directory, U directory. Okay. So the type of this object here is Unix directory. Okay. The object here is Unix directory. Okay. Now there are certain number of operations. Okay. So what operation? One is the root operation. Okay. So the slash represent a root operation. Okay. So slash operation is going to return what? A Unix directory. Okay. So the object here is Unix directory. Okay. So that means when you apply this, going to give a Unix directory. Okay. That means that's a root directory. Okay. So ultimately it's a root. Okay. So when you say root, that means so it's also a directory. Okay. Now there is another operation can be make directory. That means mkdir. Okay, in the Linux. So if you wanted to create any directory, what you try to do? You write this make directory command. Okay, and then what you try to create? What are the two things that you usually see here? So one thing is that you giving a Unix directory. Okay, that means where you wanted to create that particular directory. Okay, so right, so when let's say if you are at if you are at a current directory or the present directory. Okay, so usually what you do is by applying a make directory, you just give a folder name or the file name or whatever may be the name you are giving. When you are giving that name, ultimately what is happening, that directory is created in that particular present working directory. Okay, so but usually, so what are the two things that you need to have? So present working directory, that is a Unix directory. Okay, and you giving a name, that means you wanted to create a directory under this directory. Okay, so these are the two things, two parameters you need to give, so that what it is going to return, again it is going to return a Unix directory. Okay, so when you create a directory, okay, under a present working directory. Okay, so you exactly what is that you are creating? You are creating another Unix directory. Okay, so that is what. Okay, so Unix directory, and you giving a name which is going to return you a Unix directory. Okay, now there is a change directory. So somebody wants to change the directory. So you are at some directory. Okay, you wanted to change, right? So you do all this thing through command terminals, right? So there, what you need going to give? So you giving a Unix directory where you are. Okay, and then you giving the another one is a id or name or string or path to which you wanted to change. Okay, so that means you giving another name or a name or a string for the path. Okay, where you wanted to change, right? Where you wanted to go in. Okay, so that means you have a Unix directory currently, and then you are giving the directory name where you wanted to go. Okay, so ultimately that is going to return what? It is going to return a, what you do, change directory. Let's say you are in current directory, in your current directory, right? So what you do, cd, you write cd and then you give a name, right? Maybe Yudhishthir. If you write Yudhishthir, so maybe within that current directory there is a directory available, Yudhishthir, okay, folder. So then you write cd Yudhishthir, then automatically you will be going to Yudhishthir dot slash, okay, Yudhishthir slash. That means you are going into that particular directory. So it is also a directory, right? So that means you are giving a path, okay? So there. So fine. This is what, okay. Now present working directory. So here also you can see something like this, okay. So you are in that particular Unix directory. When you give this command pwd, present working directory, what it is going to give you? It is going to give you the string or the name of the directory, right? You wanted to know, right? So when you write pwd in Linux, what it gives? It gives something like this. Let's say you are in the home folder, right? So it will give you like this, okay. So maybe currently I am in the Yudhishthir directory. So what it will give you? So it will give you something like this, dot slash home slash desktop slash Yudhishthir. Maybe I have Yudhishthir for a string is going to give you returning, right? So that means whenever you write this command pwd, ultimately it is going to give you the name of the directory, okay. Similarly, is name. So you wanted to check whether the directory id, whatever you wanted to see whether the directory name is a name or not, whether it is name or something else. If it is a name, okay, so then it is going to give you boolean, okay. So that means what it says, let's say you wanted to check, okay, so you wanted to check whether this Yudhishthir folder is present in the present or not, okay. So in that case, what you will do? So you will write that, you will be giving that path, okay. So when you give this path, so it will check whether that the directory is currently present in the system or not. If it is present, so then what will happen? It will give you true. If it is not present, so if that name is not present, so in that case it will be going to give you false, okay. So this can be one operation, okay. Is name can be used to see whether that name, whether with the name, whether the directory with name exists or not, okay. You wanted to check. So now these are certainly operations. So you can have many other operations, okay. Whatever the operation that you can apply onto Unix directory, that you can write, okay. So now what would be, we will see suddenly some axioms, okay. So when you give this present working directly pwd of root, so root is what here? Root is also an operation. When you apply root operation, okay, unto this present working directory, what it is going to give you? It is actually going to give you the string of that root, okay. Whatever the root path is there, so there are that root path in string format it is going to give you. You can see now, you can see from this pwd of root. So pwd, so what it is going to give you always, what it is going to return? So it is going to return an id, okay. It is going to return a string, okay. Now what I am saying, so when you give this root as a operation to this pwd, so your pwd is a Unix directory, right? And that Unix directory, okay, when given to pwd, so usually it is going to return a string, okay. So now you can see, so what it is going to return? It is going to return a string. When you give pwd of root, it is going to return a string. Now similarly, pwd of make directory d comma I. Okay, so when you apply this command, what is this make directory operation? So you are in the Unix directory D, okay, and you wanted to create a directory under this directory D. Okay, so this make directory is what it is going. It actually create a directory under D. Okay, so it is a Unix directory, right? It is going to create, but if you apply this make directory of something, what it is going to, it is going to give you, it is going to it is going to return something which is, you can see from the previous make directory, what make directory is going to return a Unix directory. Okay, so it is going to return the present working directory only. Okay, it is going to return the present working directory only. Okay, when you give present working directory and the name, so it is going to create a directory, but you are in the present Unix directory only, right? UDIR only. Okay, now if you see make dir of d comma I is going to return what? It is going to return D only. Okay, it is going to return D only. So pwd of D means what? It is a pwd of D. That means present working directory of D, because you are at that particular directory D. Okay, so now you can see here the other axioms can be pwd of cd of D comma I. That means what? You wanted to change your directory. Okay, so there is a operation cd, change directory operation. Okay, so that means you have a Unix directory and you giving the I, that means you giving a path. Okay, or you giving a path or a string where you wanted to change your directory, where you wanted to change, right? You wanted to go to that particular directory. That means, so this will be going to return what? It is going to return I only. Okay, so cd Unix directory I. If you see that operation, previous operation, you can check cd Unix directory, and if you apply id, so you will be going to a directory with that is a Unix directory, but it is taking you to that particular directory. Okay, so ultimately it is with the id. Okay, so the directory with the id name is returned. Okay. Okay, so now this is equivalent to pwd of I. Either you see this or you see that. Okay, so that means these are all actually rewrite rules. Okay, so sometimes I said you, so axioms, there are rewrite rules. So these are right. So this rule is exactly equivalent to this rule. So your left hand side and right hand side. Okay, so your right hand side is also is a in the simplified version of the left hand side. Okay, so you can see like this. Okay, you can apply these all to prove ultimately certain expressions. Okay, now similarly there can be a list example. Okay, you wanted to have a list of elements G. Okay, you wanted to create a list under which you can have certain operations, right? You can create a list, okay, of type G. Okay, and you can insert okay, an item into the list with index I. Okay, so that means you giving a list, okay, to which you wanted to insert what is the index I. That means you have a list of elements. So the list of elements can be indexed with like this 1 2 3 4 5. Okay, so it is very similar to array list. Okay, so in Java programming language there is a concept called array list. Okay, so at with any index point you can insert an element and you can remove an element, you can retrieve an element, check what is the elements that are there in the list. So this sort of thing, right? So now you can specify list also. So there is an operation called insert. So you wanted to insert an element or an item into a list at ith index. Okay, let's say you wanted to insert at location number 9. Okay, So that is what. So that means you giving list and the index and the element. So which is going to return you again the list. Okay, so the list with inserted element G. Similarly, if you wanted to delete an element, okay, so you wanted to, if you want to delete an element, what you can give? You can give the list, okay, name of the list and index at which the element present in that particular index is to be given as a parameter, so that that particular element will be removed and the new list will be returned. Okay. Similarly, you can retrieve. Retrieve means what? So through this operation, you just wanted to know what is that element that is there. Okay, in that particular index, you wanted to know. Okay, so then what you need to give? You need to give the list and then the index. Then it is going to give you the element G is present. Okay, so I mean element of type G is present. Okay, similarly, so through this operation, you can see. If you give a list and if you apply this is empty, so it will to tell you whether the list is empty or not. Okay, if it is empty, so then it will give true. If the list contains at least one element, then it is going to give you false. Okay, so similarly, if you wanted to know what is the length of the list, I mean how many number of elements are there in that particular list. Okay, if you want to know that, so you can apply list. So list is a input to the length function. So ultimately what it is going to return? This is going to return an integer value. Okay, so let's say if that list contains 10 values, so it is going to give you 10. So that is an integer value. Okay, so that means int. So now this way you can create certainly some operations, and then you can have some axioms also. Okay, so the conditions. So when you create a list, so initially, so that list will contain no element. So is empty, if you apply, always it is going to give you true. Okay, similarly you can have something like this. So you have a create through which you an element, you create a list. Okay, and then you try to insert an element G, okay, into that particular list. Okay, and after inserting, so what will happen if you apply is empty? So will this is empty function going to return true? No. Why? Because now the list contains an element G1. Okay, you can think of that is the reason why it is going to give you false. Okay, so now you can have certainly many other axioms. Okay, so you can apply. So this is so now, so this is what exactly a structured specification. Writing formal specification is time consuming. So now, so you can have, you can have specifications, abstract data type specifications. Okay, you can you can maintain the structure of that particular specification is correct, that is true, but writing this sort of formal specification is time consuming. Okay, to reduce effort we need to reuse specifications. So usually sometimes you can apply generic specification. Okay, so that you can see in generic class. Have you anyone has any idea about the generic class? Generic class in C++ or template in Java? Anyone has any idea?
Yes.
Yes, sir.
Yes. What is that? Template class or the generic class in C++?
Basically, it's type independent. Like we can decide the type the function is going to work on at the time of implementation.
Right. So usually you see, so let's say for example, so you have a stack operation, right? So now instead of saying integer stack, I say T. Okay. So now that T can be changed at later while while you compile or while you run that particular stack operation. Now that T can be changed. Okay. So instead of, let's say if I want to write define the stack like this, stack of capital T instead of small, as of now I write T, capital T, stack of capital T, and then I give some value. Okay, So that means what? So this stack is going to take a value of type capital T. Now this T can be specified later point of time. Let's say tomorrow you wanted to have a stack with float number. Now the instead of capital T, in that capital T place, you can pass a variable like, you can pass float. Okay, it will become a stack of float values. Okay, and after day after tomorrow you wanted to have a stack of double values. Okay, so you pass, instead of capital T, there you write double. That means this stack will become the stack for double values. Okay, so this is what the template. So templates are usually used to reduce the effort by reusing the specification, because the specification is very same. Only thing is that only type of that variables are changed, right? So in that case, so you can use any generic specifications, right? So that's a generic concept you can apply. Incremental development of specifications, and also you can so you can keep on adding on to that particular specification, and then whatever the incremental things that you can wanted to have, you can add on to that. Okay, so that is the way that you will be able to reduce the effort, but still it is a time consuming. Okay. So this is what exactly I said you. So if you do not understand what is a generic class or a template class, you go through and read. In Java, it is a template. We say template, and in C++, it is called a generic. Okay, so you check this. So usually for any incremental development, so usually we apply this sort of specifications. So you start with very simple sorts, and then you keep on adding the specifications. So that is the way that we come up with the complete specifications if you are going through any formal methods, right? So now there are certainly some pros and cons. We'll see what is the advantages and disadvantages of this. So algebraic specification have a strong mathematical basis and can be viewed as a heterogeneous algebra. So as I told you in the very beginning, we we have discussed about these algebraic specifications. They use heterogeneous algebra. They are not going to use any homogeneous. So now you can see. So this is this can be taken as a one advantages, right? So but because it so you can see this is a very strong mathematical basis you can think of, right? So because it is going to take heterogeneous algebra. Okay, so an important shortcoming of algebraic specification, it cannot deal with side effects. Okay, so that means if at all any side effects of specifying after specifying the requirements, means any side effects with the others, when you specify something, if there is a flaw or something like that, you can think of, right, because of which it can have some side effects, right, but it cannot deal those side effects. Okay, so difficult to use with common programming language, right? So when you are going to do, so you cannot apply this with any common programming languages we today use. Okay, so that is what can be a shortcoming, because it is all mathematical and your programming languages, they are written using some natural languages with some syntaxes and semantics, like you can think of C program or C++ or Java. So they have their own constructs, right? And you cannot use combine these two. Okay, they are completely separate. So this is also, I said you, these specification these are also languages, specification languages. They also have some constructs, right? Mathematical constructs we have seen. Okay, but they are completely different. You cannot use them. Okay, so you cannot combine both. Okay, so that means you need to learn both of the things, right? So you have to learn this specification languages, as well as you will have to learn common programming languages. So algebraic specifications are hard to understand, as I told you, because of so because of the mathematical basis. Okay, so let's say if one of the property of the system is getting changed at later point of time, now you need to make many changes in other equations as well. Okay, because that is what every operations are linked together, right? So that's one of the difficulty that you can see. Okay, so if you wanted to make small changes, so that means you need to make several other changes in different other equations. Okay, so that's actually going to take more time, and it is very difficult to make these changes also, right? So we started by discussing some general concepts in formal specification techniques, and specifications have several positive characteristics. The major shortcoming of this formal technique is that they are very hard to use. Okay, so they are very difficult to use, but if you once used them, so probably they are going to reduce the cost for the later phases. Okay, so the later phases may be during design and during coding and during testing, so the effort will be minimal. It is possible that formal techniques will become more useful in future with the development of suitable front ends. Okay, so maybe we can envision that it will be usable in future. Okay, so for which you need to have some sort of front ends. Okay, suitable front ends, then only you will be able to cope up with this. So right, so we have discussed about these all axiomatic, algebraic, okay, and how we can specify these things using formally. So we have seen, right? So I stop today at this point of time. Okay, so you have any question right now? Anyone has any question related to these formal techniques?
Sir,
Yes.
sir, I have a question. This
Yes.
abstract data type you taught, that is part of formal specification, right?
Yes.
But sir, we are doing the coding in the coding phase. So how can we say right now that if you're using stack or verifying if the stack usage is correct or not at this stage?
No. We are saying is, okay, we are not going to verify by taking exact input and output. Okay, what we are checking is, okay, whether there is a type given integer, so whether it is going to return an integer value or not. If let's say we try to verify the property. Okay, property means whether that function is working, whether that is what we wanted, so usually that is giving or not, but what exact value it is going to give, that is not known. Okay, so that means, let's say, when you insert an element into a queue, okay, or stack, right? So what you want is, we want a stack again. Okay, I never said that stack will contain, you inserted 5 value and that stack should contain 5 value. That is not checked now. That will be checked during testing only. Okay, after implementation only. But what we want to know is, when you insert an element into a stack, so the stack should so it should return a stack. That is what I said you. Okay, you understand?
Yes, sir. But how do we know that we will use a stack? Like we can use some other data structure also.
So that is what I said you. That is what I said you. That implementation is not known. We are not talking about that. Whether you apply linked list or whether you implement that using arrays, I have not. We have not discussed about that. What we have discussed is, we insert an element into a stack, that is inserted. That's it. So it is a very abstract. But you see, if I say I inserted an element into a stack, but the stack is deleting an element, what will happen?
That's wrong.
That's wrong, right? So we wanted to specify, okay, want to specify our problem correctly, okay, that's everybody should understand, okay. This is the reason why we are specifying formally, because the developers are the ones going to develop these programs, right? So I said I wanted to insert an element into a stack, but the programmer is writing a code to remove an element. What will happen? That's wrong. So the programmer should not understand in that way. Okay, whatever I should say, so that should have single interpretation. Okay, so that should the coder should understand. Okay, the designer should understand the same way what I wanted to. Okay, so that should not have different meaning, right? So that is the only reason why we along with this natural language specification, we going through this formal specification also, which will complement, okay, which will comprehend, which will helpful in comprehending any complex problem, okay. So it will make it easier for others to understand, okay. But as I said you, so if you want to specify something using mathematically, so you require very rigor, as well as you require more effort, time to come up with something like this, okay. Clear?
Yes, sir.
Okay. So one more thing, so I stop the recording here and you just wait for some time.